the usual sessions comprising invited and contributory talks and the poster session. We thought of organizing this special session in order to make you, all of you have come here to give you a quick glimpse of the kind of research activities in the areas related to the topics covered by this conference at this historic institute that was founded by the first Asian Nobel laureate, who himself discovered one of the earliest fundamental quantum effects soon after the advent of quantum mechanics. So it is in the fitting of things that this institute is hosting this conference, which is, as you already heard, with an equal weightage of emphasis to experiments and theory, and both theoretical and experimental work on the focal areas of this conference have been pursued and are being pursued at this institute. So I invite Professor Urbasi Sinha, who is the organizer also, so to give a quick glimpse of the kind of research activities of this institute in this area. Welcome.
Good afternoon, everyone. Is it on? Can you hear me at the back? Okay, so it's of course a huge privilege to be able to, speak to you for a few minutes on this, occasion of the Quantum Frontiers and Fundamentals 2018. So the idea was, as Professor Holmes said, to appraise you a little bit of why we are hosting this conference. I mean, why? What are the kind of activities that are happening here which have relevance to the theme of this conference and so on. But we have a very short period over which we go over a few things. So clearly we won't be able to do justice to everything that has happened which is related to this conference, but just pick up a few things and tell you about that. So, so thank you very much to my co-organizers who actually, instilled this idea and sort of encouraged me to give this talk. So of course, for many of you, it might be your first trip to RRI, and also for some of you, maybe the first trip to India. And so that was the point of giving a little overview of our relationship with quantum frontiers and fundamentals. So, well, of course, it dates back to several decades ago when from the first pieces of work which come to mind is of Professor Joseph Samuel with Professor Bhandari, and they worked on this, Pancharatnam berry phase, and it was a very, Professor Samuel is already interjecting. Pancharatnam berry phase, yeah, of course. Yes, Pancharatnam first, and then, of course, I mean, so that sets the tone. So, just to give you an Indian perspective on things, so Sam is helping me out. So that is, of course, one of the first things and so on. And then, of course, we've had Professor Rajaram Nityananda, who's now associated with a different place, but he has done work on almost everything that comes to mind, but then optics and quantum mechanics being two very important areas of contribution that he has had. Our former director, Professor Narendra Kumar, is someone we cannot forget in this instance. Unfortunately, he is not with us anymore. But then, he actually set up the Light and Matter Physics group here at RRI, which has a lot of experimental activities going on related to quantum research. And he himself has, of course, again done most things under the sun, including biology. But then one of the things he was doing before, so that was related to the arrival time calculations, which has direct relevance again to this conference. So with that, I will go on to talking a little bit about what some of my colleagues here are doing, and then also talk to you a little bit about some of the activities in our own lab at RRI. So first we have, of course, the theoretical physics group, and two people from the theory group are very much involved in quantum research. One is, again, of course, Professor Joseph Samuel, and some of his recent areas of interest would be coarse quantum measurement, an exploration of the loss of quantum coherence due to the observer's resource limitations, and again then gravity and decoherence, which is, he came up with a simple model showing how gravity destroys quantum coherence via the Unruh effect. So this is just a little glimpse, and of course there are many more things to talk about. Then we have Professor Shupurna Sinha, who's also from the theoretical physics group. And some of her recent interests would be in entropy and geometry of quantum states, and the role of quantum entanglement in state discrimination, and they have arrived at a quantum Fisher-Rao bound. And then, of course, the Lorentzian geometry of quantum and qubit entanglement. And we heard a talk from Kumar Shivam on this during the Monday session, I think the last session of the day. So I think some of it has already been discussed in this conference. Now, next I go on to the light and metaphysics group, which is a dynamic group, I would say, consisting of 6 of us. So there are 6 faculty members, and all of us are interested in experiments as well as theory. And some of us have more connection with quantum research. So I will begin with Professor Hema Ramachandran, who is working on quantum logic gates using cold atoms, as well as classical sources with tailored photonic statistics, among other interests that she has. Then we go on to Sadiq Rangwala, who is a quaint man. He is working on quantum interactions and dilithium, and of course, these are some of his setups. And what they are doing is, of course, they are not really working in quantum information per se, but then, of course, they are working on things which require quantum mechanics at a very basic level. So we have the ion atom molecule light trap, and then ion cooling mechanisms, ion atom interactions in the quantum regime, cavity QUD, non-destructive measurements of ions in cavities, and so on. So this is more a cold lab run by warm people. Then we, of course, have Andal Narayanan, who's here with us in the audience. And she is heading the quantum optics lab at RRI. And her main area of interest over the last few years has been electromagnetically induced transparency experiments with rubidium atoms. And so lots of applications under that. She's also interested in weak measurements, both theory and future experiments, and theoretical understanding of coherent cyclic interaction of atoms with fields. So these are the 3 members from the light and metaphysics group who are working on various aspects of quantum mechanics in one way or the other. So next, of course, I will go on to our own activities for a few minutes, and that would be the Quantum Information and Computing Lab at RRI. So we call ourselves the QUIC Lab. And all of us have very interesting acronyms, by the way, you may have noticed. Quaint, QUIC, so on and so forth. So then the Quantum Information and Computing Lab started when I joined RRI in 2012. So we've been here now for 6 years, and the lab has been functional for 5. And so what we are doing is, of course, our lab is dedicated to research in quantum information. And so various aspects of fundamental aspects of quantum mechanics, quantum computation, as well as quantum communication. So that kind of is the basis for the, it sort of has direct resonance with the theme of this conference, which is quantum frontiers and quantum fundamentals. So we have also a quantum optics lab, which is a class 10,000 clean room. And it has less than 10,000 dust particles per cubic foot. That is what a clean room means. And we also have another lab which we will go on to hybrid quantum computing. So the whole idea being that we want to have a precise control on temperature and humidity in our lab, because as you have seen over the last 3 days, the weather conditions can be unpredictable, and the dust conditions as well. So we don't want to be affected by that in our little lab. And so we are primarily dedicated to quantum information, computation, and communication. So this is how the lab looks, and of course this is just Wednesday of the conference, and we have 2.5 days more. So please, you do contact us if you wanted to see the lab and so on, and the experiments that are inside. So these are the areas, as I mentioned. And of course the lab, the picture that you saw was empty, but the lab is hardly empty, So we have lots of very enthusiastic students who are working with us in different capacities, and various people have, of course, worked with us and gone on to greener and not so greener pastures. But then, we've had an inflow and outflow over the last 6 years. And so these people would be the ones who directly come to my mind, because I'm sure you've seen all of them either in the T-shirt or in the bag or in the food department. So all of them are members of the LOC of this conference, or they are volunteers. So I must say that, of course we have a thank you session in the end of the conference, but this conference does, owe a lot to the enthusiasm shown by these students outside the lab for a change, So this is the constitution. So now, of course, I'll spend the next 5 or so minutes telling you a little bit about different experiments which we are working on in the lab. we have quite a few going on right now, and some have just been completed and some are in the process of completion, and we are going on to other things. So this is an experiment on manipulation of entanglement sudden death. So it sounds daunting, of course, but then the whole idea is that, you know, entanglement, I think almost every alternate speaker has talked about entanglement, so we don't need an introduction to that. But it's a very important quantum correlation, we are aware of that. And what we want to do is hold on to it. We don't want to let it slip away. But of course, it has a mind of its own, and it has a dynamics of its own. So it is going to decay as a function of time. And so there are two ways of doing that. One would be an asymptotic decay, which is okay. But the other one would be at a finite time if it goes to 0. And that is called sudden death of entanglement, when it goes to 0 at a finite time. And we want to change that time and make it happen later, so that we have more fun with the entangled state in the form of applications. So that is the idea behind manipulation of sudden death, and we want to manipulate it and have it happen later. But of course, we can also make it happen earlier, because they come together in some sense in the operations. We have a poster on this outside by Ashutosh Singh, so please feel free to discuss more with him on this. We already have a paper on this, on the theory of our experiment, and he's almost finishing the experiment as we speak. So this is one area. Then, of course, another experiment which we are very happy about is, a purely, I would say, a quantum optics experiment, which is on the demonstration of a homo-Mandel dip. So we talked a lot about HBT, Hanbury-Brown twists in this conference, but not so much about the HOM. But HOM, as you know, when you have two indistinguishable photons, which are incident on two ports of a beam splitter, then they like to come out either one way or the other. So they create the 2-0 or the 0-2 state. So if you measure a correlation between these two ports, you get a dip for the when there is no time delay between the photons. And this is a classic quantum phenomena. And so we have an HOM dip from the lab using near-infrared photons, which is almost around 97% visibility, which is actually, we're very happy about that. And so this is a part of a bigger project, which has other aims and is in collaboration with Professor Barry Sanders, who's the director of the Institute for Quantum Science and Technology in Calgary in Canada. And so this is going to be submitted shortly. Next, we go on to, well, of course, this is a very interesting and important topic for this, for the current purpose, because this forms the basis for the conference. So as I told you in the inauguration talk, we got this grant from the Templeton Foundation, and that was for our research in generalized measurements and weak measurements. And a part of that grant is this organization of the conference. So this, some results from the same exploration have happened. This is an an idea in which we have inferred expectation values of non-Hermitian operators using weak values in a Mach-Zehnder interferometer. So this is a mouthful, but in some sense it's a very neat experiment, and Surya is going to present a poster on this right outside, and this is in collaboration with Professor Arun Pati, who of course is an expert on weak measurements. So this is another poster. Then we go on to, so see, the idea is that this is on quantum frontiers and fundamentals. So we have talked about some of the some of the interesting applications we are working on, but then we cannot have something without quantum computation in it, because of course that is one of the most interesting technologies that quantum mechanics is applied to. While of course there is a lot of research going on worldwide on quantum computing using qubits. So you all know what is a qubit. This is a learned audience. But then what we are focusing on is slightly different. We are working on what are called Q-trits. So this is a higher dimensional quantum system. I think Arvind mentioned it in his talk yesterday. So the idea is that, if you have a two-level system, you want m number of that to have that exponential power. So 2 to the m is what we talk about when we talk about this exponential power of a quantum computer. But when we have a 3-level system, it becomes 3 to the something. So 3 to the n, let's say. And we know that 2 cubed is 8, 3 squared is 9, which means that 2 Q-trits have similar access to the Hilbert space as, let's say, 3 qubits. So with a smaller number of a higher dimensional system, we can be expected to, play around a lot more towards our quantum computing application. So that forms the basis for this work. But of course, we started this while I was still at IQC, and of course, 2 of my co-authors are right here again in the audience, Thomas Jennewein and Piotr Kolendersky. So this was the first paper we had in which we showed a single Q-trit using the spatial degree of freedom of a single photon. And we played what is called the Aharon-Wadman game and achieved the quantum advantage and so on. But now we have taken this forward in our lab here at RRI, where we are actually working on producing bipartite Q-trits. And so this is a picture from the lab. And of course, there's a poster on this by Shubhajit, who is also somewhere here in the audience, or maybe, yeah, he's there. And so this is very interesting, because now we have a bipartite Q-trits, which are not only spatially correlated, but also in very recent work, which is a theory work in collaboration with Professor Dipankar Home, who's the co-organizer for this conference, and experiments which again involve Piotr and Thomas. We have been able to show that these bipartite Q-trits are nearly maximally entangled. So we have found a new measure of entanglement for quantifying entanglement in a higher dimensional system, and applied it and found perfect match with experiments. So then this is a lot of interest to us, this particular work. And so then, so this is, some of it is on the archive, some of it will appear shortly. But so this is an area which we are very interested to pursue further experiments. All right, so now this is quantum frontiers and fundamentals. So in a frontiers aspect we covered a little bit. I will now switch gear to the quantum fundamentals. And of course, this is now a very interesting thing to talk about, and very easy, because I think every alternate speaker again has spoken about the superposition principle. So I think that was introduced by Thomas even today. So then I don't think we need to discuss what it is, but what we will tell you is what we have done towards it and correcting its application in interference-based experiments. So this is more in sync with the fundamentals aspect of this conference. So then, of course, so what is that? So again, there is a poster on this outside by Rengaraj, who's a former student in the lab and going to Germany next week to pursue his PhD. So what are we doing here? So we have, okay, so double slit. Previous talk gave such a nice photon story, but I'm not going to take her to court. So we will just remain in this auditorium here with the photon, and so it could be any other particle, by the way. So we have a double slit, and what I'm saying is that we have a source, we have a detector, and the question that we would ask is that if the solution to the wave equation when the single slit is open is psi A, and if I close A and open B and call the solution psi B, what is the solution when I open both slits together? And so this is the usual assumption we make, that the solution is psi A plus psi B. But of course, this is not true, because these are three different boundary conditions, also three different Hamiltonians. You just can't simply add 1 and 2, call it a solution to 3. And so this is something which we have assumed in many textbooks and ourselves, in fact, for a long time. And then it led, so in a collaborative work with, again, Sam and Shupurna, we actually found a correction term in terms of the path integral formalism, which also was discussed this morning in an interesting way by Professor Sokolovsky. But then, so this is the path integral. And so here, I already tell you what is going on. So if I have two slits open, I have the possibility of a path like this, which wouldn't occur if they are open individually. And so these are the paths which do not extremize the action. And we termed it non-classical paths in our paper, but then just think of it as a sub-leading contribution to the solution. So then this was the work we did, in which we quantified this in terms of path integral, and so on. And yeah, so I will skip what is path integral for you, but the whole point is that an integration over all possible paths can be taken by the particle in going from A to B, and this all possible forms the basis for what we have done. And so this video, if it plays, sort of sets the stage. So the idea is that, if you have a source and a detector, you would have paths which are crossing the slit plane once, and these are the ones which will extremize the action, and we called it classically dominant or classical paths. And then you would have paths of this kind. This is just an illustrative example, which actually do not extremize the action, but they are still there, because of course path integral allows all possible paths. And so paths of this kind which do not extremize the action also contribute to the propagator. And so this is what would be the subleading paths. And this will be completely missed if you just added them individually. Only if you open them together will these probabilities start creeping in. And so this is something now it would seem quite natural to you. And so this brings us to this quantity, which is called the Sorkin parameter, which actually captures this correction term. The Sorkin parameter will be a 0 if these paths do not contribute, and it will be a non-zero if they do. So you just need to either quantify or measure the Sorkin parameter, and you would know whether what we are saying is right or wrong. So that was the idea. And so this, we don't have too much time, and so we will basically I'll just tell you that this is the algebra which you have to believe, which is very trivial. So if you have all three slits open, then basically this term is just all 3 open minus the 2s plus the singles, and this will turn out to be 0 under 2 assumptions. One is that probability is following the square law, which is the Bond rule, and the other is psi is psi a plus psi b plus psi c. So there are 2 assumptions which go into making this a 0, and so of course we are questioning the second assumption in this new series of work that we have been doing over the last few years. So we had already, I was involved in the first experiment which measured the Saltine parameter. At that time we had measured it to be a 0. And now I took the parameters from the same experiment and saw what happened with the new theory, and thankfully they were 10 to the minus 5, and our resolution at that time was 10 to the minus 2. First thing you do is not negate your previous result. So that was the motivation behind taking these parameters. And then we went on to actually using electron parameters. So the idea is that the theory is independent of the particle type. So it could be photon, electron, or anything else, neutron, so on. So then we went on to actually getting an analytic bound on this formula, which is very important because you see all that is okay, but you need to know whether it affects you, whether when you are doing an experiment this will matter or not. So you need some length scale dependence going on in your mind, and so this formula is the maximum contribution that the Saltine parameter can have in a given experiment, lambda being the wavelength, d is the interslit distance, and w is the slit width. So this is the maximum contribution. So then even if you don't want to follow the rest of it, remember this formula because it's important to know. And so we had very nice match with finite difference time domain simulations, and of course those simulations took that kind of resources and hours. So sometimes simplicity is nice is what we proved with this second paper. And then of course, yeah, so I always would like to apologize to half the audience because they would be theorists and so on. But then we have very friendly people here, so you would agree with me on this, that if you can, you might want to do the experiment. And so that is what is important, and there were different experiments done. One is an example here. Again, that was a 0 for the Saltine parameter. And this experiment, which was released around a year ago, was from the Boyd group in Rochester and Ottawa. And so they used a single photon experiment, and what they did was they used a gold film and etched these 3, 2 and single slits and found the Saltine parameter, and this was their result. So there are a couple of things which one has to note here in this experiment. One is that the gold actually led to the production of what are called surface plasmons, which led to this enhancement in kappa or the Saltine parameter. It wasn't a length scale dependent experiment. So it was not true to the spirit of the original Saltine formula that I just showed you. But the second most more notable thing would be that if you are not yet, you just had tea, that was the idea that you're awake during this talk, so then you would realize that these are the experimental data points, and all of them are negative values, and all of them are actually at the dip positions of this graph. So this is supposed to be the theory graph, and these are the experimental points. And what is interesting is that the experimental points do not really match the graph in entirety. So if you are a skeptic, you would say I could just fit another kind of function to explain this data points. So indeed we think that we could do better, and we were parallelly doing better, and we went outside the lab too. So it's RRI. I'm sure the people who are new here would really appreciate the ambiance that we have in this institute. So we used it to our advantage and started doing experiments outside the lab. And so this is the field you might have seen in your walks around RRI. And so we have a horn antenna as a source, a horn antenna as a detector, and we have slots now. So this is a macroscopic version of the experiment. But you have to realize that this is fine because we are only testing boundary conditions here. We don't really need a single particle to do that. It's a boundary value problem. We can solve it using electromagnetic waves, which is precisely what we are doing here. And so then we, of course, weren't satisfied because here there are some garages and with cars and so on, which reflect electromagnetic waves back to the antenna. So we had to find a better location, which is 100 kilometers from RRI. So yeah, I know, it's quite a story, isn't it? So 100 kilometers from RRI, there is an observatory called the Bittner Observatory, where most of the radio astronomers are doing their experiments. But because we have them also as collaborators here, they gave us a part of a field. And so we set up our tent there, literally. And so this is the final version of the experiment, which is, you know, free from the winds and the elements. And also there is a corn field here, which is a very good absorber for microwaves. We realized over the 2 years that we did the experiment. So yeah, so these are the parameters, very different from the ones you have been seeing in the other experiments. This is our radio astronomy friend. And so this is the schematic, and of course important is this graph. So this is what would happen if what we are saying is not true. So this is a 0. 10 to the minus 15 being the level of precision of Mathematica. And this is what we measure. So these are the experimental data points with their error bars, and the blue is the theory. And I would say, I would actually venture to say that this is a much better agreement between theory and experiment than just negative values below the axis, right? So then this is, so these are different examples of experiments we have done at different length scale regimes to show the same thing. And then of course, when you say that you've measured the Saltine parameter to be non-zero for the first time, you yourself are skeptical of what you're saying. So in order to satisfy maybe even yourself, we went on to do an experiment in which we killed the effects of these parts. So we actually put absorbers perpendicular to these slots. These we call baffles, as a result of which you can see that contribution from such paths would be diminished. And as a result, and as you increase the baffle size, the kappa value is expected to go down both in theory and experiment. So this gives us a tunability parameter that we can actually turn on and off the effect due to this correction term to the superposition principle, which actually sort of makes it very, very unambiguous what we managed to do. And so this is the idea. So it's the first quote unquote observation of the non-classical paths in experiment in a classical domain, bear in mind. And then baffle experiment is the tunability. And Feynman path is now equally, so there is a second person now who's advocating Feynman paths on the same day, but I'm not, I'm also in favor of weak measurements. So then, so this is the idea that it's equally valid in classical and quantum regimes. And the whole point is Saltine parameter was never meant to be zero anyway. So you have to figure out how to do these bond rule experiments better. So first you have to worry about things which will naturally make it non-zero. And then beyond that, you might want to think of how to modify bond rule to explain things if, as and when it happens. So I just spent a few minutes on this because this is very much the fundamentals theme of our conference. But then I'll go back to the frontiers now for the last slide. So in the last few months, what we have started is, of course, very, very exciting to us as a lab. We have a project with the Indian Space Research Organization, which is, of course, our space agency, on quantum experiments using satellite technology. And, you know, so this has started roughly 3 or 4 months back, so we are in the initial setup phase. But this is a long-term project for us as an institute and as a lab. And as a first experiment, we are hopeful that we will be able to share a key between India and Canada. So Thomas Genevine, of course, gave a wonderful introduction to quantum experiments using satellite technology this morning. So there is no need for any further slides on that. That was a great talk. But then, of course, the idea is that, you know, this is a huge distance that we want to sort of scale literally upwards. And so this would be one of the first things we hope to do in this project that we have started. And we do have, you know, bilateral collaboration and so on. And so this would be something to look forward to in a few years' time, hopefully in collaboration. So this is right. So I think I have covered most things that I needed to say regarding the various things happening at RRI as well as our lab on quantum frontiers and fundamentals. So with that, I would like to thank you. And so this is a group of visitors at different times. And you can see many familiar faces here in the audience. And so I would like to keep changing this slide with more and more people and holding this conference more and more often at RRI. So thank you very much. Thank you, Professor.
So we have some time for comments or discussions or any questions you may have.
Yeah, even in the morning.
It's only now occurring me to ask you, how, what's the path length involved? So to the bounce to the satellite and back, what's that length?
This is hopefully going to be a LEO satellite, right? So it will be like 600 to 700 kilometers, I would say.
One way or both?
One way. And then the satellite has to move over to the other ground station, which will be in Canada, hopefully. And then similar.
That's cool.
Yeah, I think so. Yeah, thanks.
So actually, I'd like to ask about the Baffle experiment.
It's baffling, right?
It's baffling, and I was wondering, so you indicated that one of these sideway paths is blocked, but couldn't you just get additional new ones which go around those paths?
Yeah. So that's a very good question, actually. So the idea is that, you know, so in that second paper that I mentioned, we have proven that the maximum contribution to kappa actually comes from what we call the hugging paths. So the hugging paths are those which have minimum kinks. So indeed there is one kink here and one here. So those would, and as you increase the loop, so to speak, you can actually, of course, approximate it with many kinks, and then the contribution exponentially drops. So indeed we would have more, but they will not really make it a larger quantity. So they would be more and more subdominant is what we had shown. Yeah. So this hugging path is kind of prevented. Yeah. It's an absorber. So this is a perfect absorber. So whatever it is, it's not going to.
So this Sorkin parameter would be 0 exactly if the contribution were orthogonal, right? That would be the
Sorkin
case.
parameter, so that's again a good question. So the Sorkin parameter is a modulating function, as you can
So
see.
in this case, it's different from 0 because the different slits are not orthogonal situations, right?
No, Lorenzo. So the point is, it is 0. So the Sorkin parameter can be 0 and non-zero. So it's a modulating function. It will cross the 0 line, as you can see.
Sure.
So what is happening is, so at a certain detector position, we have different contributions coming in from the triple, double, and single slit patterns. And so they would add and subtract to being 0 at regular intervals. But they wouldn't always do that as a function of the detector position. So that is what
Sure.
they do.
I guess what I'm saying is, if the slits would indicate completely orthogonal situation, it would be always 0, right?
What is the meaning of completely orthogonal?
I mean, if instead of having psi 1, if psi 1, psi 2, psi 3 represented orthogonal states, then the Sorkin parameter would always be 0. And you wouldn't have
so
this.
then there won't be any interaction anymore, right? So if there, so what you're saying is a paraphrasing this only, right? So if you open up all of them, then you have the possibility of these, let us say, these secondary waves actually meeting and causing some difference. But if you just had them blocked, so we have a simulation on this, where we have actually just put blockers in between, and then they represent the perfectly orthogonal situation, and in which case nothing will happen. Yeah.
Okay.
So, but yeah.
On your next slide over with the baffles, back right there. I assume you did this, but when you put the baffles in, I assume the intensity goes down. So did you normalize that out? And that's why the Sorkin parameter drops, or is the normalization taken care of?
No, normalization is always taken care of. So it's, and in fact, the baffles are perpendicular, so it's not really affecting it much. They're perpendicular to the plane. Yeah. Yes.
So I was wondering how difficult this would be to do same experiment with single photon. Is it too difficult, or?
No, it is not, because it has been done by the Boyd group.
They have done, but
but not very well. But it could be better.
No, because when you deal with electromagnetic waves, then talking about which path it goes through may be slightly, confusing. I mean, waves can go through all the paths all the time, right?
No, but this is a Feynman path.
But
so it's a Feynman path.
No, whenever you think of path, you think of like a particle, right? So particle can go through this slit or that slit, or can go around this slit. But if you're dealing with the wave, then it can go through all this slit at the same time, right?
Sure, but then of course you're talking about the path being taken by the particle. And what I'm saying is that this is of course a Feynman path. It's a probability amplitude for this, that, or all three happening. So that is the same. So if you do the simulation which we have done, so there is no difference between the single photon and the electromagnetic wave simulation. It's just that if you want to do simulation for electromagnetic waves, we have used a very dedicated electromagnetic wave solver, which takes into account all the inadequacies of the experiment, like the size of things, material, and so on. So that is a different story. So if you do just path integral, you won't capture that. It will be more ideal than that. But then there won't be any difference as such between using the single, because of course the path integral calculation that we had done was for a single particle. So we do not expect to see any, but then of course they have done the experiment using single photons. And so then you can see that, so the theory looks very similar. It's a modulating function with different periodicity. But only, it would have been nice to have data points elsewhere.
So why? So in this case, why they don't match?
We can email them.
No, any idea? Any?
I mean, of course, what they do say is that they don't really have the. So see, this is an arbitrary unit, so we can't say much. But these things must be very close to each other in actual position. So they're not able to resolve very well between neighboring points. So they don't really get anything there. So they are only able to measure when they have maximum values. So these are actually maxima, right? Absolute value is. See, negative and positive, only difference is of course the sign, but these are the maximum values that kappa can take, and so that's what they're able to measure. But somehow they don't have the precision to measure in between. But
No,
it's a
in
good
your
question.
case, it matches very well. So
I agree.
yeah. So
Yes. Thank
Okay.
you. Yeah.
Show that picture with the baffles and the picture with the baffles and the hugging paths, please.
Yeah.
So this time you're not showing paths which are circling around the
Yeah.
aperture.
So as I mentioned when I was showing them, those are representative paths to bring forth the point, but those are actually subdominant compared to this hugging path.
But these paths require that one doesn't seem to require the existence of an open slit over there.
Sorry, which one?
That path, if I completely closed off that second slit,
Then this path will survive. Yeah, that is again a good point. So these paths, which actually are still loopy, but do not actually cross the slit plane more than once, all contribute to the classical propagator.
how can there be an effect if there's no second slit over there?
Sorry, what can you repeat that, please?
How can there be an effect if there is only one slit? Why is there the notion of a hugging path at all?
The notion of the hugging path, it's not a notion. Sorry, I don't follow you.
Okay, maybe we should talk about
Maybe we
this
should talk about this later.
separately.
Yeah.
Thank you.
Okay, so if there are no more comments or questions, so we thank
Thank you
the
very much.
speaker once
So-
again.
Yeah.
And